a little bit later, so I'm sure all of you will want a red ticket if you didn't get one. So he will be walking around as Andrew starts.
No, I think I'm going to use this microphone. Thank you so much, Judy. Thank you all for coming out here. And I want to, before I forget, I want a big thank you for Two Brothers Brewing and the Roundhouse. Big thanks to Charlie, who's helped out, and big thanks to Chris from Two Brothers. How cool is it that we have a brewery in our own neck of the woods that not only does science cafes, but also makes beer like Adam Smasher Ale. Is that not cool? Am I right? Yeah? This is what I think is really cool. So that's not me. I'll get this. All right, here I am. All right, so I do want to, just before I really get started, I'm going to try to explain a little bit that Anthony and I, or Tony and I, are going to keep our comments relatively short because part of the idea of the Science Cafe is that we have discussion time. All right, so if I don't go too deep into it, it's because I'm trying to keep my comments short so we can save time for discussion. All right, and I'm also going to start off first not by talking about vinyl records right now, but I'm going to talk just about sound waveforms in general. All right, so here I have a representation of three sounds. I'm going to try to play these and hopefully have you listen to them, so I hope this works. All right, cool. Cool, so I'm going to do that one more time. All right, so by looking at this, I'm not sure if many of you would have been able to tell me what you're going to hear, but I think most of you can identify that there were three separate instruments that were being played there, right? We had a violin, a trumpet, and a piano that were all played. And part of what is interesting to me, as someone who specializes in the study of the physics of musical instruments, is that all three of those instruments were playing the same note at the same amplitude for roughly the same amount of time, and yet everybody in this room was able to tell the difference between those three sounds. And that musical quality is what we call timbre. Now, I'm not going to talk too much about timbre, but I will point out that, from this slide here, and just from that idea, I could spend the next 10 or 15 minutes easily getting deep into the weeds of that. And we don't have time for that, so I'm going to move on. And I'll tell you, one of the things that I did a lot when I was a lot younger, I liked playing around with sound recordings that, I was pretty young when computers were fairly rudimentary, but I do remember the ability, once I was able to get access to a computer, I would take a sound file and try to zoom in on it. So that's what I want to show you what this looks like when we zoom in. Now, I do want to point out, you probably can't see this, I have a time scale up here. This is the time, and then this is an amplitude scale. You guys can't see the numbers. I'm so glad that none of my students are here because I didn't put labels or units on here. So that's our little secret. Don't tell my students. All right, I know. But I'm going to zoom in right in the middle here on this one at about, this is the trumpet, it just happens to be at about 1.8 seconds. That is just for our reference. The time is meaningless here. But when I zoom in, I think you can see that there's some detail that we couldn't see from the overall view. So we can start to see that this waveform has a repetitive nature to it, but it's not a smooth sinusoidal waveform that you might see in a math textbook or anything. It's very complicated. And again, I could spend 10 or 15 minutes just on this, talking about that, which I think is really interesting, but we have other more important things to talk about tonight. So I want to keep zooming in on this waveform, and the detail becomes more obvious the more I zoom into it. And I get to this point here, and I don't think that you guys can see it. Maybe somebody in the front can see it, but what I start to see here is that this program that I was using is plotting individual dots on the screen. And I exported this and I replotted it so it'd be more obvious for you to see. You'll note that the feature of a big spike and then some wiggles and then another big spike and some wiggles, which repeats, that's what we're looking for. And so I plotted that exact same thing, wiggles, then big spike, wiggles, and then big spike. But this is the exact same data. And my point here is that when computers make audio recordings, if I press record on my laptop and I record the sound of my voice, what the computer is recording are hundreds of thousands or millions of individual measurements of the amplitude of the voltage that the microphone has transmitted to my computer. All right? So this is completely not at all like what vinyl records do, and this gets to the essence of the basic difference between records and, well, not records, digital music, for example. All right. So I want to talk a little bit about what you need to think about when you're sampling, when you're making samples. Each one of these dots, each one of these amplitude measurements is what we refer to as a sample. And so when you go to sample a sound source and make that recording, what do you really, really need to care about so that you get a good recording? All right. So let's talk a little bit about that just for a few minutes. All right. So here is a hypothetical sine wave. This is what in the language of music or language of acoustics, we would refer to this as a pure tone. That is, there's just one frequency in there. If I played this tone, it wouldn't sound very musically interesting, but it's really simple for us to talk about. And again, I didn't put the axes on here at all. This is even worse than the previous graph I showed because now there's no numbers, there's no nothing. But again, imagine that time is going horizontally and amplitude is going vertically. All right. So I boiled this down to just 3 repetitions. All right. So if it starts here and goes down, a repetition occurs when it goes down again and comes back up. So there's 1, 2, 3 oscillations in this hypothetical sound wave. Now, if this is a signal, like a speaker is outputting this, and we're trying to record it, but we're going to make discrete individual samples, we should think very carefully about how we do that. All right. One strategy might be in this 3 oscillations that we just make millions and millions and millions of samples that are nanoseconds apart from each other, and we just reconstruct this out of lots and lots of samples, which would be great if our electronics could support that, if our data storage could support that, and sometimes it can, right? But not always, all right? So that's one extreme, thinking about what if we just throw everything we got at it and take as many samples as we can. On the other extreme is, what if we made one single sample for every oscillation? Every oscillation gets a sample. What does the sampled waveform look like? All right, well, this is what the sample waveform would look like, this black dashed line. All right, now, if your real waveform is this red line, this is your real sound, and your reconstructed that goes on the CD or on your computer or whatever is this black line, that's really, really bad, right? You have completely undersampled what you need to do. So, okay, let's increase it just a little bit. And instead of making one sample per oscillation, what if I make 1.5 samples per oscillation? All right? So instead of doing 3, I'm going to do like 5. All right? Well, this is what that would look like. All right? So I have a sample right here, a sample here, a sample here, a sample here, and a sample here. And if I try to fit a sine wave that goes through all that, it's a lot better than the straight flat line that I had, but it doesn't match the red line, and we in fact have a completely different frequency than what we had before. All right? And so this kind of gets to the issue of, well, what, is sampled music as pure as true analog music? All right, so I'm going to show you one more hypothetical. If we go to 2 samples per oscillation, if I have a sample here, 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 then I can, if I fit a sine wave, and I pick these locations just for convenience, then the dashed line here, which is my sampled sine wave, matches what the true sine wave is for this. All right, so I'm going to jump back really quick to connect this back to this trumpet waveform. So with these samples, some people might say, well, how do you know that between any 2 samples there isn't an amplitude that you just happen to miss? All right? And the answer is, I don't know. Maybe I did miss it. But what we come up with when we get to this level here where we said, all right, two times per oscillation is what I need at a minimum to be able to get a reasonable sample. And then anything over 2 samples per oscillation is just making my ability to match the original wave, it's just making it better. Right? So if I had 4 or 6 or 8 or 100 or 1,000,000 or whatever, it would just get a better and better reconstruction of the original wave. But this 2 times per oscillation minimum gets to something that is known as the Nyquist theorem. That's the famous, and I promise, this is my physics side coming out. I promise this is the last equation in the talk tonight, all right? But you're welcome. Yeah. I mean, if the equation is too much, just order another round, right? But so what this says is that the maximum frequency that you care about needs to be no bigger than half the frequency of the sample rate, all right? So in other words, if your sample rate, if you're really trying to figure out your sample rate, you need to move this 2 to the other side of the equation and say, well, I need to sample at a minimum 2 times the highest frequency that I care about. And for humans, the range of human hearing goes from 20 hertz to about 20 kilohertz, 20,000 hertz, all right, at the high end. All right? So 2 times 20,000 hertz is 40,000 hertz, or 40 kilohertz, which is very, very, very close to the sample rate for CDs, compact disc. And so if you understand this, which I fully recognize, I'm backing in to talking about vinyl records by talking about CDs. But what I'm wanting us to think about is that the fact that vinyl records are an analog medium, meaning there is no none of the sampling, that doesn't just simply mean that it's inherently, therefore, better. All right? Because your ear can't perceive the frequencies that are higher that would be missed by the sampling. All right? Now, that doesn't mean that vinyl isn't preferred for some other reasons, which I'm going to talk about later, but I want you to really have this idea in your head. So, all right, so to accurately sample waves commonly in the range of human hearing, 40,000 samples per second. That's what I said. I forget what's the exact sample rate. It's
44.1.
44.1, right? Exactly. And what's interesting about that is a power of 2, which makes it really, really convenient for computers to deal with. But that, again, that's another, like, we're able to make this movie using an electron microscope. The process by which they make this this video of the needle going through the record, that the needle is being dragged through, and you can see the needle wiggling back and forth, and this needle is going to send a signal back up into the cartridge, and then through the arm and into the record, and get amplified and all that. And it occurred to me as I was thinking about this quite a bit, is that I was, from my youth, I remember, records are stereo, right? But the record player, the turntable, only has a single needle. And it occurred to me that I had no idea how that magic happened, all right? And I think it's really cool. So before I talk about that, I'm going to try to show you a very, very quick demo, and then I'll show you that how that works, and then make a few more comments, and I'm going to turn it over to Tony. But really quick, my demo, I hope you can see this, because this is the biggest thing I could get for this demo. This is what we call a galvanometer, which is a fancy way of saying it measures electrical current. That's all it does. And right now, I have nothing hooked up to it other than a coil. This is a coil of wire that's just wrapped up here and hooked up to it. There's nothing, it's not plugged into anything. I promise you, after I get done talking, you can come up and inspect it. Nothing's going on. But I have a magnet, and if I bring the magnet close to this, then the needle deflects. And as I bring the magnet away, the needle goes the other way. So there's some really interesting physics here, but the point is that by having the magnet and the coil interact, I'm causing an electrical signal, which this thing is measuring. And I could hook up that electrical signal to a needle, and I could make that needle go back and forth, or I could hook an electrical signal to an amplifier and hook the amplifier up to a set of speakers, and then if I wiggle this fast enough so that you can actually hear it, then we'd have sound. And that's essentially what is happening in the tiny little cartridge of the record player. There is a magnet and a coil, and they're moving based on the grooves that are going back and forth, and that signal is what's getting amplified. All right, but how does it work to be stereo? And it turns out that there's 2 coils and 2 magnets in there, and I just am really, really impressed by that. So the groove of the vinyl record, and I apologize if you haven't been able to tell, I like vinyl, I really do. I like records and that sort of thing. I'm not a vinyl guy, so when I don't use the right terminology, forgive me, all right? But the needle going through this groove, it's actually a V-shaped groove, and so if you can imagine one side of the groove that does nothing, and the other side is wiggling back and forth, then only one of these magnets is going to move in this coil. And so all of the signal is right here. All right? And you have just one channel going. Alternatively, if this side is doing nothing, and the other side is wiggling back and forth, then all the signal is going to be in this channel. All right? And so what's interesting is that if they're both wiggling back and forth, these are completely independent. So if they're both wiggling back and forth, then they're both going to be sending a signal, their own signal, to the different channels of the sound system, and that's how you get the stereo recording. And when I saw the elegant simplicity of that, I was just blown away, and I was like, that is so, so cool. And there's this whole history with the strategy of how the grooves were encoding the sound, because for a short time, the encoding was at the bottom of the groove, and there was some playing around with the encoding on the side of the groove, and it's a really, really fascinating thing. So I stole these graphics from Joe Collins' YouTube video. I highly suggest you go and check that out. All right, so last thing is I want to give you a little snapshot of where the current science is in terms of why it is that some people prefer vinyl over other media, right? And it turns out that science has a really, really hard time of assessing preference, right? I mean, I don't know, why are some of you drinking the IPA and some of you are drinking the lager? I don't know. Probably because some of you like hops and some of you don't, you know? But why? I don't know. That's really, really hard to measure, and it turns out even when we can sort of measure it, it's usually, you know, population dependent and not, you can't make general conclusions on it. What science can measure is things like the amount of perception of emotion. All right, so there are studies which look at people are presented with the same musical sample from different recording media, going like back to the early parts of the recording history all the way up through MP3s. All right, and it turns out that all the different types of recording media will easily be able to convey emotion. All right, so that's really interesting. What's also interesting, I don't going too much into that, but is that since they're all easily able to do it, there doesn't seem to be a lot of difference with their ability to do it. All right. You can test for does the recording convey a perception of age, right? Like, can you tell, was this recorded yesterday? Was this recorded, 60 years ago, 100 years ago, whatever? And it turns out that definitely the recording media does make a difference. All right, so people are very, very sensitive to that when it comes to the type of recording media that was used. And then also people can easily tell the difference between quality. And quality is another thing that's hard to define, but we can come to some definition of it, and you can say, well, there's a difference between the early types of the quality from a wax cylinder, for example, versus the early vinyl records versus modern vinyl versus music on YouTube, for example. All right. But the thing that I want to leave you with is a relatively recent report. This is from 2014, and it was a study that I think kind of confirms what some people had already guessed or suggested, but there's some evidence. This isn't hard science. This is very preliminary, but there's some suggestion that in your brain there's a strong connection between your auditory system, where you're processing the sound, and the part of your brain that controls motor function. And the authors of this study, they pointed to how, well, there's a certain actual mechanical motion that goes into placing the record on the turntable, and then taking the needle and putting it on the record. And you don't get that same experience by pulling out your cell phone and clicking play on Apple Music, right? I mean, there's so little tactile, kinesthetic connection with the modern devices as opposed to the previous ones. And so when you have experienced the mechanical part much earlier in life, then your brain makes that association with the music that you experience. And so when I saw that, it was like, oh, that's science talking about why what everybody else would just talk about the nostalgia factor, right? And to me, it's really, really interesting that there's this connection in the brain that is connecting those two parts, which previously I think we would have said are somewhat disconnected from the experience of sitting and listening to the music, right? All right, so I want to stop talking for a little bit and bring Tony up and hear from him. So thank you.
Hi, everybody. How's everybody feeling tonight? All right. Hot for some analog discussion, as Judy alluded to earlier. Just get this here, talk a little bit about myself. I do work at Northern Illinois University. I've been there for almost 15 years now, and I work as an audio engineer. And some of you people, a lot of you people may ask, well, what is an audio engineer? And just off the top of my head, if I can just get a couple quick responses. First thing you think of is audio engineer. Anybody? Live sound, sound reinforcement, good. Any other ideas? Studio, recording engineer. All right, so there's a couple examples right there. And lo and behold, my next slide, look at the first one, sound guy, right? Everybody's least favorite person when things don't go right? That's me. I wear the hot seat. I sit in the hot seat all the time. Another thing that we do as audio engineers is design and implementations of equipment. Now that could be anything from studio design, monitoring, or some work that I've done with the university, including classroom support. So we develop models that would work across platforms across the university and what they call the smart classrooms. And develop a platform where everything, for teaching purposes, everything is uniform and a professor can go from one place to the other, and hopefully it's going to work. And the next thing somebody said was recording specialist. So that's kind of my bailiwick. That's where I have the most experience. When I started this a long time ago, I worked at a radio station, Carl Nelson. Not the same one as Carl. I started in a station in Rockford as a production guy. I'm just kidding. I actually started as a painter. But since I was reliable and showed up on time, and if you know anything about the radio business, that's a rarity, they hired me to be on-air talent. So that's where I got my first introduction to production and audio methods and engineering and all that stuff. Now, along the way, I've kind of built a resume, including this production specialist. I'm integrated with a team of talented videographers and producers. I am their audio guy, so if they have audio issues, which in the field, recording always comes up. There's always something that I can find wrong with something. And it usually has to do with misalignment or having several microphones at different distances, creating all these phase-related issues or HVAC noise or compressors and things like that you hear. So my job is to take care of all that stuff, get rid of it all out of the mix, and just deal with that true sine form, that S wave that we were looking earlier in Andrew's presentation. So along with all that, I also am I'd say the majority of my work is editing. So I'm in a studio environment with a controlled environment with a calibrated system of monitors, which is also very important, and I'm just going to stop right there for a second, and I want you to think about this. At home, or let me just ask this. How do most of you enjoy your media, and music in particular? Is it at home? Is it on a headset? Is it on a computer? I'm just curious. Favorite phone? Phone? Did I hear phone? Oh, yes, the phone. So what I'm dealing with and what we're talking about here in order to get things really down to the nitty-gritty, I have things in a studio, you're able to control these relationships between time and distance. the time that a frequency hits your ear, and by the time the other frequency and the other one hits your ear too. So differences in those time and space relationships end up creating kind of a, if you will, a 3D atmosphere of what you're hearing is designed as a human. So let's go on to the next slide here, and I'm going to regress once again. Why vinyl? Why the resurgence? Why the thing, right? Why is it such a huge topic right now? Well, this is my grandmother Gladys. Grandma Gladys is 98 years old, and this picture was taken a couple of years ago. But over the holidays, I had an opportunity to spend Christmas with her. And Grandma's 98, so she suffers from dementia and a few other things. So her thought process and her presence awareness, you guys can hear me all right? Okay. All right. I'm trying to use my speaking voice. So let's go back in time and talk about Grandma Gladys. So when I saw her over the holidays, she would have little lucid moments every now and then, and she wouldn't really remember my name when I walked in, but she remembered my face, right? And her face would just light up when I walked into the room. So, and she couldn't recall my name. I had to tell her who I was. I'm like, oh, Tony, your grandson Tony. And she's like, oh. Well, about a half hour later, we were having lunch with her, and she was hopping around, reliving memories in her mind, just random thoughts that would pop up. And, 1 minute she was out in the potato fields. My grandmother never worked in the potato fields. But, she'd go from one story to the other. And then something happened. She stopped cold in what she was like, whatever it was that she was thinking about. And she looked at me. And this look came over her face. And I'm like, what is it, Grandma? And she says, you're the little drummer boy. And I thought about that. And she's like, remember the records that you used to play when you come over? And I'm like, well, Grandma, I was a baby, but I do remember. I do have a recollection of that experience. One of the most magical experiences of my early life. Listening to Frosty the Snowman, the Burl Ives version. Yeah, I see a lot of head shaking going on. You know that record. And Rudolph the Red-Nosed Reindeer. And don't forget the little drummer boy. Now, I was a baby. But as soon as she mentioned that, and as soon as she looked at me and said that, I instantly could hear those records. I could hear, quote unquote, that experience. And it was something that was shared between her and I. And it was something that I don't think necessarily we come across every day. It doesn't really come across in the digital media. And I think this has something to do with what Andrew was talking about, these psychoacoustic properties, if you will. There is something tangible to having a record, right? You do have to make a choice. You do have to put it on something. You do have to turn on an amplifier. You do have to have a set of speakers. You do have to have all these things lined up in a space that makes sense to you. A place where you can actually kind of take it apart. We don't always get that same deliberate thought process when we're listening to an MP3 or maybe listening even to a CD. To have that something instantly, immediately recallable, that immediate gratification that everybody wants something faster and better than what it was before. Well, what are we losing in that? We're losing those feelings. We're losing those connections. Those connections aren't there. I'm not really making a choice thinking by hitting a play button. Yeah, it's the same thing, but is it really? There's nothing to hold on to. An MP3 is not tangible. I can't grab it in my hand. I can grab an iPod. I can grab a phone, but I can't grab my record. A record, when I look at it, I open it up, it's got words. Oh my God, there's words. There's stuff printed in there. There's credits. There might be art. There might be other things. And yeah, you can get digital downloads for art and you can read that stuff. But any of you vinyl collectors out there? Anybody? I see a few. High fives, I imagine you guys all high fives, yeah. So, So let me back up a second. Again, I don't have a huge hi-fi at home. I don't have, a $25,000 turntable. It's not built on a 3-foot slab of granite, which you can get. You can get the big granite stone where it weighs, 2,000 pounds, and it calibrated. Everything is, lined up. Most of us don't have those resources. A. Number two, we probably don't really care that much. Because what we get out of it, we already know what we like about it. We already understand that when I drop that needle, it's going to do something, right? And I'm going to like it. So back to Grandma. After that experience over the holidays, it really got me thinking about this. So let me just move on here. I joke all the time to my wife and my kids about squiggly lines. They ask me what I do all day. Carl's laughing. So this is an example of some squiggly lines. Now what we have here is a simple diagram, and this is a phase meter essentially. So what we're looking at, if you think about this, and let's go back in time again, and think about how our ears work. Okay, we hear in our ears and our brain has this amazing ability to take information, and not only information, but differences in information, and assign them different relativity and importance. This is how we develop our hearing. For instance, if I were suspended in this room, if you could just picture me being suspended in this room, I should be able to hear in 360 degrees, all around me, right? Above me, I can distinguish the sounds up there, if it's coming from behind the bar, if it's coming from Carl's table, if it's coming from behind. I'll quit bashing on Carl. I love Carl. You guys know Carl Nelson for WNIJ? He's over here filming, yeah. Give it up. He does a lot of good work for the area. Thank you. So what we're looking at here, this is really interesting. This is the kind of thing that I will spend, I don't even want to tell you how many hours on. But if you kind of look at this triangle that's facing down in the green part there, what we're looking at, so say this was a stereo image, which it is. You can't really tell it in this diagram because it's only measuring one. But we are looking at a left and right composite image. And what we see is kind of this area where if you're dealing with loudspeakers, you're dealing like this stage, for instance. I have 180 degrees plane here, right? And my ears are focused here. So that's kind of what this is representing. This is exactly what's happening now. I'm here at this point, and then you're out there at the top of the triangle. So the sound is traveling in different ways because you're in a different position than you are, for instance. And it's taking different times. Now, what happens when you mix that? What happens when you have two or more things competing, like a vinyl record? Remember the example from the left side of the magnet going up and down and that translating to another wave, and then the right side hitting this way? What happens? Something magic happens in this relationship. So the idea, and this is what I correct most times during the day, I want to see things like that triangle. I want to keep things, quote unquote, in phase. That means I don't have the amplitude at the peak of one wave when I don't want the bottom of another wave or a similar wave at the same time as that peak. Because guess what happens? Anybody know? They cancel each other out. Very good. Now what happens if they're a little bit off? One's a little ahead, one's a little bit behind. What happens then? Anyone got an idea? Well, I'm sorry, I can't hear you guys. Echo. Okay. Time. Okay, so there's a relationship there. Very good. That's a good place to start. So there is a difference between that time that frequency is displayed here and where it's going to be. So what happens, and this is where the math comes in, and this is where I step out, by the way. I'm not a scientist. I am an engineer. I do this for a living out of more interest than anything else because I'm fascinated by it. But if you look real close, you don't have to look that close. You see the stuff that's going on outside that triangle? up close to the azimuth on the horizon there, on that 180-degree plane, those are phase anomalies. Okay? Normally, and this is kind of goes with production techniques and going into a little bit of engineering. Back in the day, when they were first, not first, but say pre-modern recordings, which I would say probably date back to the early 70s when they really started experimenting in these things. They really didn't care about this stuff out here because those were relationships that the engineers and the people that were designing the records and recording them, and the artists to a certain extent, people like Lou Reed was an early pioneer in doing binaural and sound field recordings. So those kind of recordings have a lot of this, what's called anti-phase. Now that's a term that I'm using for this display. It's not really a technical term. But basically what it says is there's frequencies that are outside of that 90 degrees that I'm expecting to hear. I'm expecting to hear that in that 90-degree sound field. Now all of a sudden, or back in the day, you might listen to an old jazz record, maybe some Miles Davis or something along those lines, where you hear that really wide field of separation. You know, the saxophone is over here, the keyboards are over here, or maybe this is another good example, the Beatles record, right? So this is great. They were working with 4 tracks back then, right? So they had 4 different things that they could do. Well, so what did they do? They developed these placements of different voices to give you that spatial representation, that field. What else did they do? They isolated things, right? They took the drums, right? Ringo's got 4 drums up there and a couple of cymbals, but where are they in the mix? Anybody ever like turn the balance over one side or the other during, you know, I don't know, Sergeant Pepper, say? What do you get if you turn it all the way left? Anybody? You get drums. You get drums, right? You may hear a vocal. You may hear the reverb tail of a vocal. Okay, great. What? That doesn't make sense. So I turn the balance over to the other side. What do I hear? Well, I hear a bass. I hear George, George Harrison. I hear the real voice. Now, all of a sudden, when I put it back together, what do you got? You've got both of these things, right? But what happens in the middle, in here, causes this relationship outside. Let me get to my next slide. What happens there is you're introducing artifacts. So, let's talk about that. I mentioned a little bit about human hearing and binaural recording. If you're not familiar with binaural recording, there's lots of stuff out there. You can go really deep on it too. But think about this. Binaural, we hear binaurally. That's how our brain works. It takes the information, one ear, the other ear takes the information, and somehow our brain magically melts those two together, and it sounds like stereo, right? So this binaural study, if you will, the deeper that you read into it, you start to look to see what are these phase relationships? Why does it sound so much different in stereo? Anybody have a sound bar? Anybody mess with those? You got a few sound bar people over here. What that does, and this is just strictly layman's terms, it takes a stereo image, so your left and right, and introduces an algorithm. So without getting too technical, there's a lot of phase inversion and properties and functions that I can't even, and theorems behind that, but it has to do with inverse phase relationships, and that's kind of where the magic is happening. You don't see it. You don't see it coming out of your speakers. You don't see it when you listen to it, but you can hear it. You can definitely hear. How about any Jimi Hendrix fans out there? Yeah, everybody loves Hendrix, right? One of the first examples of this kind of these phase relationships and manipulation of these phase relationships is the thing that I found and other people have found. And again, you can go on and go pretty deep on this stuff. There's a whole dark, deep state of audio. mean, you've heard of the deep state. Audio is even worse. I think it's even deeper because there are people that are really, really passionate about this stuff. And a lot of research was done and has been done, over the years by different countries. Germany and England, two prominent countries that have done a lot of research into this talk. So, without getting bogged down and mucked up in too much of the details, there's these things called interaural level differences and interaural time differences. These are those things that I'm talking about in your head. They only happen in your head. There's a mathematical equation that compensates for the delivery of a signal coming from, say, this side, which would be on the right side. There's a difference between the time of when that hits here to when I hear it with my left ear, right? Why? Because my head is blocking it, right? So a sound wave comes in here, my head's in the way, I can't hear it over here. But what do I hear over here? It's usually a reflection, right? So that reflection, that time that I'm listening now over here, is now over here. So there's that difference. There's also the difference that happens in your head. Because of the spacing, if you picture your ears as microphones, and if I had a binaural head, that would be the perfect example to show you this. But basically, it just looks like a robot head. You've probably seen them. And instead of ears, they have microphones built into it. They're fantastic. So what that does is replicate the binaural concept. It simulates how we hear. So when you get into immersive audio, which I like to call it, those relationships become heightened. These phase differences, let me go back one. These phase differences here, things that are out of phase, will become manipulated, right? So what happens then? It's a really interesting thing. Is it just vinyl, right? Vinyl introduces yet another set of variables, which we've talked about. And that set of variables has to do with these differences in time and differences in how I hear. So an audio engineer might say, okay, this is great. I'm going to put the vocal, pan it all the way in the right side. Now I'm going to take this trail, this reverb that's coming at a different time, and I'm going to put that way over here on the other side of the mix. Well, what did I just do? What just happened there? And how is it that my ear can discern the difference and know that, hey, the vocal's over there and there's a reverb tail over there, right? Those manipulations of those differences in phase and time relations are the thing that makes vinyl so magic. And is it magic? I don't think so. It's not magic. We have science that can play. We saw the electron microscope. You saw how it works. You saw how things happen. But, again, when we introduce all these differences in time and differences in frequencies, we have what's called crosstalk. So imagine, if you will, and this is a really kind of basic example, but anybody heard feedback? I cover the microphone, feedback. That's a form of crosstalk. That's signals that are normally looking to be their regular sine waves, right? Well, they happen to be lined up with something else that's happening. And it's created a new point, right? Because now we have artifacts. We're introducing more frequencies to the original frequency. That's one of the things about vinyl that I think often gets overlooked, because even if you don't have, say there was a record with nothing on it, there was no music on it, okay? And if you played that record and then looked at the frequency assessment of that, you'd be able to see that on your scale from signal to noise, say 0 dB being the highest point and minus 70 being a nice floor, barely audible to most people. When you play a record, depending on how good your machine is, and depending on how good your equipment is, and depending on how calibrated your monitors are and your equipment, you're going to probably see something. You're going to see something where there's stuff going on and it's bouncing around from the very low frequencies, say 10 hertz, even all the way down to 10 hertz. You're going to see stuff going on, and you're going to see stuff going on well beyond the 20,000 hertz, 20K. There's stuff going on even 30, 35,000, 40,000. If you look at records, that information is there. There's actually stuff, you can measure that. And I would consider that a noise floor. So when you think about that in a speaker trying to replicate nothing, I mean, there's actually something that's going through there. It's finding grooves, but there's no music, so to speak. There's still something there. You can turn it up, you can hear it. You might hear static, pop, static, crackle, pop, you know, all this stuff. And if you look at, if you go back to the scope, let's go back here again. I like this slide. This is my most fancy slide. I took it with my iPhone today, so yeah, I spent a lot of time on this one. But what you'll see with those crackles most of the time is they're going to be way out of phase. Like way either to the right or to the left. Maybe sometimes you might get something that actually falls into that triangle where we're expecting it. But for the most time, this is wavering. So whether you're listening to a vinyl record at 33 RPM, or 45 RPM, or 78 RPM, there's going to be these artifacts that are there just from the physical medium that's there. And those artifacts, those differences, where those frequencies are lining up, even though they're not part of the main signal, they're not as loud as, you know, the guitar solo at the beginning of the All Along the Watchtower, for instance. But they're there. And not only are they there, they're affecting and leading to and building on this idea of crosstalk. And through that idea of crosstalk, again, the manipulation of these harmonic frequencies, if you will, derived from, say, a stereo source, you end up with this beautiful thing, three-dimensional audio, which I'm not going to get too much into. I do want to mention it because well, let's just go on from here. Let's go ahead. This I stole from the internet, and I'm sorry for not crediting. However, it does have labels. So, Andrew, just so you know, so these are those time differences that I was talking about earlier. This is represented here. So here we have a sound coming from the left. And this is only from the left. It's just to help identify what's really going on physically. And then on the right is what you would hear. The right is your right ear. And as you can see, the peak of the top one, it's kind of close. These two are kind of close. But what's that difference? That difference is the time that it takes to go from one ear to the other. Right? There's a difference there. And just that little bit of difference is enough to see, well, you're like, oh, it's kind of in phase, it's kind of not. Well, look what happens on the loudness scale. So we're talking about timing and timbre. There's another word there. I drew a little bit too early. The timbre. But if you look at the loudness relationship is much more one-to-one. Right? You can see here, I'm looking at the second chart from the top, that line is in phase with that line. Great, what does that mean? Right? And so what we're looking is we're able to perceive the loudness a little bit closer than we are, say, the timing. Right? Because we don't have that difference. That whatever it is, that loudness, it's in the same. It's the same for both of them. And now, look here, we're talking about timbre. So, or timbre. It's timbre. It's timbre tonight. And I should know this, I'm a musician, right? I know about timbre and pitch. Look what happens. You can see that it's kind of fuzzy. It's not quite as well defined as the loudness recognition, but our ability to discern what that trumpet is, you know, from the violin or whatever, it's a little bit fuzzy. Well, now we look at this 3D stereo effect. It's the combination of these three things. And this is happening in your head. There's mathematical science behind this, including one of my favorite terms, the cone of confusion. And have you heard about that? Anybody? They have, like it couldn't be more confusing. They had to actually call it the cone of confusion. But basically what it is a complicated function and explains this relationship and what happens here. And the anomalies that you're seeing here is what making us recognize spaces coming from either left, right, forward, back, up, down. So vinyl does a good job of taking all this good stuff and then screwing it all up. It does. It does. You can hear it. And how many of you have like played a record with not even the volume up? Can you hear it? If you listen close. If you have a really awful turntable, like one of those Sears things in the box from like 1976, you can usually hear it across the room. It sounds like, right? Right? So there's a mechanical addition, something going on in that actual needle going back and forth. It's making a sound. It may not be louder than what you're listening to, but it's making a sound and it's there. And I bet if you concentrate, if you go home tonight, you put it on and go, oh my God, I can hear that. Just turn the volume down and listen to your record. I bet you can hear it. So there are all these things happening. And these convolutions, when manipulated, make this magic thing. So what is the difference between the analog and, yeah, right? My NIU folks are laughing here because this is a picture of my office. This is where I work, my workstation. It's actually a very early picture because you see I still have a tape machine in there. But basically, this monitoring system is set up, for me, it's calibrated, which means that they're spatially positioned in the room to create a 5.1 mixing field, or a surround sound mixing platform. So, and I've got some other closer, other monitors there that I use for like critical listening as well. Not everybody has this. Not everybody's going to notice these differences. Not everybody has a tool, you know, a spectrograph to be able to look at these things and go back and say, well, what are all these differences? But real quickly, one of the main differences I think we have to address with the resurgence of vinyl is this likability, like you discussed earlier, Andrew. This perception. It's really hard to quantify things like that, right? Well, given that we talked about these phase relationships and how differences of them, you know, have spatialized and taken context and taken content and created this magical field. And we know about the noise that a turntable will make. You know, if you have a great turntable, it's going to be less. If you have one like mine, it's going to be more. But one thing that we can kind of attribute the resurgence of vinyl, which I guess is a good way to put it, is this thing, listenability. Back in the day, when I started, after I worked at a record store for many years. When I started getting into this, I started looking at signal to noise. And basically a signal to noise ratio is basically, if you think of the quietest part of a performance, that can be measured. And if you look at the loudest point of a performance, that could be measured too. And we measure this on a relative loudness scale called decibel units, right? So when I look at an audio, say CD, or even a DVD audio with greater resolutions than 44.1, what am I looking for? I want to see the maximum signal ratio over that noise. I want something like 10,000 to 1. That means for every decibel my content goes through, it's 10,000 times louder than the softest nothing, where I don't want to hear it. Well, okay. That's in an ideal world, but we don't measure at 10,000. We have a scale from, you know, minus infinity to 0 dB on the digital scale. So when you look at a vinyl record and look at the loudness of it, and I'm talking about the integrated loudness, you're going to find that it's going to be, when you stack it up and zero out and meter everything and calibrate everything, you're going to find that in general, it's quieter than content that's on a CD. Why? Anybody have an idea? Hey, there's a winner back there. Who said that? All right, this guy right here. That's right. So back in the day, when they were compression, and overabundance use of compression. So vinyl engineers and people that were recording a long time ago, they weren't concerned so much with making that signal absolute the loudest thing that it could be. What they were looking for was dynamic range. That range between the highest point and the range between the softest point. Now this becomes really important in classical music, right? Because if you think of a classical music piece, you've got a whole bunch of dynamics. It's not going to be the same in a, I don't know, Blink 182 record, right? Right, so what they're looking for, what they were going for were different things. So even modern day produced records, they still make them. They are, you can get them. There are people, I have a friend who, he's on his second kid, and the first one he put through college, and the second one is almost through, and he's been doing nothing but selling records for the past 15 years. Now his wife works, and she's got whatever, but he's actually made a very good living from this. So what I'm trying to say, or what I really mean to say, and the differences that we perceive, is when we use this compression in the digital world and making everything loud, and we make it as loud as it could possibly be, guess what? I don't want to listen to it for a long time. Why? Because I get exhausted. It hurts my ears. Listening to something at that level of amplitude, that high, hurts after a while. And I do the same thing when I put a record on. Guess what? That drops significantly. You're probably not going to see a peak in a record if it's calibrated, measured, above maybe minus 4 dB. So that is the biggest difference that I can see, or two of the biggest differences that I can see, and why there's this warmth and general kind regard that's associated with vinyl. But it's those artifacts. It's distortion. It's mechanics. It's electronics. It's perception. It's that emotional and physical connection, right? It's not just this is sine wave is happening here and this sine wave is happening over here. No, we're going through all those things. We're going through those memories. We're going through those thoughts. Your records probably smell. You probably recognize that smell, right? Everyone's had a musty record. So, without getting too much further in the weeds here, I'm going to leave it at that and turn it back to Andrew. And what I'm really interested in is finding out your perceptions and your thoughts. So if there are any questions, I think this would be a good time to start. Thank you. And if anybody would like to contact me, I do have my email address up here too. Feel free to take a picture of it. I'm sorry about the non-contrast font. That was the last slide. I kind of screwed that up a little bit. Hi, Judy. Thank you for having me.
Well, we enjoyed hearing you, and we're going to have questions in just a few minutes. We're going to take about a 5-minute break so that you can use the restroom or refresh your drink or whatever. Get to know the person near you. By the way, if you come back to other STEM cafes, we do sit at each other's tables, so feel free to do that. Is there anybody that didn't get a red ticket?
Anybody not get a red ticket?
There are a couple people up there, Jeremy. Oh, okay. All right, so we're going to take care of those people, and we're going to have a little drawing at the end and one in just a couple minutes. I'm going to be running around with this microphone, so make sure that I'll be running upstairs too, so somebody will signal me if somebody up there has a question.